Now, this one here is taken from Patankar's book, and he addresses this additional diffusion. Of course, he admits it that yes, a first-order upwind scheme is very diffusive. Now, he didn't like the word that other people were using about his programs, saying that it was a lot of false diffusion. So, if you can recall, I named them the two diffusion mechanisms. I named one numerical and one I named artificial, just to differ. The numerical, that was the problem child, that was negative. You had got a negative diffusion inside or in front of the double derivative. That was due to the first order Euler step in time. So there we had a negative diffusion. And here, with a steady state code, we have the sort of the demand cell Reynolds number must be smaller than 2 to keep the viscosity, the total viscosity positive. So the numerical part, that's the negative part, negative diffusion. The artificial, that's what you get from choosing a sort of an upwind scheme. That's the artificial part. Now, false diffusion then is something totally else, and according to Patankar. And then you will see an example for it here. It's to do with the mesh, how the mesh can make a diffusion mechanism. So from the previous example, if you let the viscosity be 0, then you are left only with the transport term, only the convective term, only. That's all you ever have. Meaning you don't have any viscosity, you don't have any double derivatives, you shouldn't have. Meaning if you have a problem like this, you send in a constant velocity, and then you have hot and cold fluid, then they actually shouldn't mix. You don't have any diffusion mechanisms. If it's temperature, of course, it's not viscosity, then it's the little k, thermal conductivity. And if that one is 0, you shouldn't have any mixing at all. This should be the correct solution for all times, for all spaces, when the flow goes to the right. So you should keep this sudden jump. And here, if you simulate this one, now with the first order upwind scheme, of course you get that. Because the first order upwind, with no double derivative, he just picks the value to the left when the velocity is positive. So of course then you get the very correct solution. With the central scheme, it can't be done at all when you don't have any viscosity. He will be negative, he will just explode. That's actually not entirely true, but in general it is. So, for the first example, just uniform flow in the x direction, not a problem. First order upwind scheme give you the correct solution. Yes, it does. Now you flip the flow 45-degree angle. So we're going to simulate this one later. Ferziger has the same example. So now the flow is entering here, 45-degree angle. And we have given the hot side here, the boundaries are given, and here 0, the cold side. And the solution should have been, without any diffusion, a sharp jump. So here at this line, 50-50, that's okay. But then you should immediately have 100 here and 10 on the other side. Instead, you see you get this smearing effect due to the mesh. And this is what Patankar calls false diffusion. I would still say that this is due to the terrible first order upwind scheme, that you get this smearing effect, regardless of the mesh So I don't buy his arguments completely. You'll see that afterwards when we look at the example from Ferziger. So that was Patanka's idea what is false diffusion. So the upwind scheme, as I say, I call it an artificial diffusion, just to make a difference here. You add some viscosity, and of course then for large cell Reynolds numbers, local Peclet numbers, it can be okay to have it stable, but you have to know what you're doing, because then the viscosity you're actually solving, it's a totally different fluid. And yes, Patanka agrees also that for small Peclet numbers, the central scheme is absolutely more accurate than the upwind scheme. Of course it is. But he claims for practical real-life cases, the cell Reynolds number is going to be too large, and then you can't use the Taylor series at all. Here it's sort of a comparison between different schemes, with different value of the local cell Reynolds number, the Peclet number, and then you have specified the boundary values from 1 and 0. And you have an exact solution for this very simple problem. So it should be nice and smooth, something like this, depending on the Peclet number. We have actually seen this example more or less already. The first order upwind scheme smears it out. The central scheme goes something like this. So as soon as you go outside 2, then you start getting negative values here, and on the other side 2, you get values bigger than 1. Then here he is outside sort of the bounded region where he should be. So the central scheme, very good indeed in this region, but quickly very bad indeed when you go outside for values bigger than 2. You can construct hybrid schemes. You use central difference if the Peclet number is small enough, and then you jump to first order upwind if it's not. But that's not so good. You have higher order upwind schemes, power law. Here, just by chance, he hits the exact solution directly. You have several of these more modern schemes, fourth order upwind, third order upwind schemes. You have many of them. So I won't go into details there. And of course they are in use because the problem remains. Cell Reynolds number is big. Okay, you have to do something. You can't use pure central differences. Something has to be done, clearly. So a higher order upwind, that could be an option. Other options. Nowadays, we have a lot of computer power available. Remember, this book was written in the early 80s. So the computers were very, very small, very slow. So nowadays, easier just to use a lot of delta x's and delta y's to get the cell Reynolds number smaller. Use unstructured mesh. You create a mesh system then that sort of follows the flow. That would be beneficial if possible. And choose a numerical scheme that make this diffusion smaller than the real one. And Patanka then concludes central differences can't be used in practice, especially when viscosity is 0. But then you are talking Euler codes. That's not so interesting anyway. Although a lot of people are using Euler simulations. The guys who build airplanes, they're using Euler codes. Think about that the next time you take a plane. We have another way around this. Add the time derivative in front of the convection diffusion equation. Although you're interested in the steady state, you can still use time development. If you do, then the demand for the cell Reynolds number changes. Then it has to be smaller than 2 divided by the Courant-Friedrich-Levy condition, then a Courant number. And the Courant number, that's your choice. Okay, the mesh is given. Here you have the local solution of your velocity, but you can choose a very small delta t. That works perfectly. I did a direct numerical simulation once, and the cell Reynolds number was around 50, which then would be terrible. But in that simulation, I had to use a very small delta t anyway, because I had to resolve the turbulent time scale, the Kolmogorov time scale. So I ended up with this ratio being 1.25. So that was okay. But using a steady state code, it would have exploded. My cell Reynolds number was around 50. Okay, any questions so far or comments? Then I'll stop with finite volume here. We will have a peek into it in the book by Ferziger. And it should be down here somewhere in chapter 4, I believe. Yeah, this was the classical example we looked at earlier. Sort of exactly the same layout, and yes, you have an analytical solution to this one. And yes, if you violate the stability criteria here, the cell Reynolds number is bigger than 2, then central schemes gives you very unrealistic results. The first order upwind give you a result, yes, but with a very big output. So here then Ferziger addresses finite volume methods, and he starts correctly, I would say. You set up this integral equation directly. That's where you start. There should be the starting point. So you have here a convective term, and here you now have the diffusion term, and then maybe you have a source term somewhere inside your problem. So how to define your mesh system? You have a lot of choices here. Where should you put your unknown? Should you use a staggered mesh system like we had in Sola, pressure in one point, velocities in different points, or like it's said here, it's a co-located mesh. You have all the unknowns in the center. That's quite popular these days. Much simpler, not so much bookkeeping. And the problem with using co-located mesh was initially that you could have a pressure field which was very oscillating, sort of a checkerboard pattern, where the pressure neighbors, they don't talk to each other at all. But today you have several ways, several workarounds that problem. So here you have a slightly stretched mesh in both x and the y direction, and then it is a question, where should you put your center point, your nodal point? Should it be in the cell center, or should it be sort of that this distance is equal on each side? Here it is not, but here it should be. Same distance here and here. Your choice. Doesn't change the accuracy either way. So that really doesn't matter. And of course, we have to rewrite these integrals in algebraic expressions. So yes, you sum up all the faces that you have around your cell. The notation in 2D, east, west, north and south, and then southeast and southwest and so on. And in 3D, you will have the top and bottom as well. So classic notation all the way. Then, yes, I won't go through all this integral practice. He then differ between what he called a CDS, a central differencing scheme, and an upwind interpolation scheme. So here you will find the first order upwind, and also examples for higher order upwind as well. So here, CDS, linear interpolation, UDS, upwind. Quadratic upwind, quite popular, but a little bit dangerous as well. You're using 3 points, so it should be second order accurate, but with this one also you risk getting some errors. Nowadays you find even higher order schemes, which is actually quite okay. But this sort of beyond the scope of this course. Boundary condition, equation systems, and then finally a cute little example. So let's just jump to the examples. So it's the same equation as we had, diffusion, advection and diffusion, or convection and diffusion. And then we create a 2D case for this one. So here again, the only unknown we have, that is the quantity phi, whatever that might be. For simplicity here, I suggest imagine it is a sort of a concentration of something. So it's a transport of some material, following the flow with the velocity, and the velocity is given. We know the velocity field, density, the diffusion constant, large gamma, is a constant. And the velocity field should be stated here somewhere, isn't it? Yeah. It's a classical 2D case. X velocity goes like x, y velocity goes like minus y. So the stream function will be x multiplied with y. So the streamlines will be, say, hyperbolas, y equals 1 over x. So the flow solution will look something like this. We know the velocities. So here are the streamlines. And then we only look at the first quadrant and say the y-axis is a solid wall. Down here we have a symmetry line. And then we have a possible flux, a diffusion of this quantity phi into the stream through the wall here. We send in just 0. But here we have an increasing value of phi from 0 to 1. So we will have some diffusion of this quantity phi, whatever it is, into the flow. So that is our problem. Fairly easy to program that one. And now we will try with both a UDS and a CDS, upwind and central scheme, to simulate this one. So then he goes through all the different fluxes needed to do the simulation, which we will skip and jump directly to the program. So it's a cute little MATLAB program for this example, so I'll put it out for you so you can play around with it. And I have set up some cases how we can solve it with the different parameters. So, but feel free to play around with other cases as well. So I just use true or false if I want a central scheme or a first order upwind. So I have here a 100 by 100 case now. And we then need to solve an equation system. So here I'm using the SOR, successive over-relaxation. So I set it up as an iterative solution procedure. So I can show you here the left boundary. That one is given, so not a problem there. So he's just stated once. Then I need a lot of coefficients, depending then also if it's a CDS or a UDS scheme. So here I just followed the recipe blindly from Ferziger. And then finally we do the iterations. So we have to find a solution somehow. And the equation system here for the entire domain, just given by, if you can recall, the modified Newton-Raphson for SOR. You calculate a residual, which then, if everything is okay, he should be 0. And then you use the arrow, the residual, to adjust your phi according to this recipe here. You divide by the derivative of the center point you're looking at, and that should now be the coefficient AP. And then I calculate the adwood as well. So he will stop if we have an overall adwood smaller than a given number here. So also he stops if the adwood becomes too big, then he has exploded. So let's try this one. So now I have CDS scheme, central differencing. I have quite a small gamma. I have 100 points, 100 by 100 case. Then I can't use, as you see here, I can't use an over-relaxation at all. He's becoming unstable. I have to use under-relaxation. So I can show you if we run this one. So this now is with the central scheme. So these are now not the velocity field. The velocity field is given. These are contour for the value of phi. He changes from 0 to 1 here on the wall. So here you'll have close to 1. So clearly, yes, we get some diffusion into the flow, and it's transported like this. And this one looks fairly close to the one that we have to the left up here. Gamma equals 1/1000. So yes, we can get this solution, not a problem. But if I go a little bit above here, omega, actually he could take it. That wasn't my idea. He should explode. A little bit bigger. 4. And there he exploded. And strangely enough, he gets the problem up here. I have no idea why. Here, you don't have any fees at all. You have fee 0 coming in from the top all the way here. Why the heck should he have problems up there? I have no idea. But that's where sort of the disturbance starts. So to make a solution, it's a steady state solution, you have to be very careful. You could have solved the equation system here using a direct method, but I think you might be in trouble using direct methods. I think he's so jumpy that he can easily explode. So using an under relaxation, yes, that is quite more like it. Using fewer points will cost you even more. Actually, then you really have to use an under relaxation, only 10% adjustments at every iteration. Strange. Increasing the gamma, that sort of softens it down. Remember, you divide by this gamma, the viscosity, to create the local cell Reynolds number. So when gamma is big, then it's more and more stable, of course. So small gamma, that's the problem. So a bigger gamma, then we get a solution fairly quick. So now I can go back to the bigger omega. 1.7 should be stable. We get some noise, but it gets filtered out, so you find a solution in the end, which then looks very much like the solution to the left here. So yes, we have actually not that big a problem with the central scheme here. If we had continued to decrease the gamma, smaller and smaller gamma, you will, with the central scheme, be in very big problems. You can't find a solution. Now, jumping to an upwind scheme, we could do the same. CDS 0. So if we go back to the first case here, now you see I can actually use a much bigger omega, finding a solution much faster because this one is much more stable. So not so easy now to tell that this solution from the first order upwind scheme is not the same as the one we had with finite difference with central scheme. That's not so easy to see. It's there. This one is much more diffusive. It transports more phi, unnecessary much into the domain, but you can't really see it here. You can play around with this one yourself, put them on top of each other, these two solutions, if you like, then you can see the difference. The way you can see it very good is looking at the anode. And also here he looks at the total flux through the left wall. So that one should be exactly at this number. And then, depending on how many cells you have, you will be quite off, as you can see. For the central scheme, then you have a certain minimum amount of cells that you have to do to obtain a solution. For the upwind scheme, the dotted line, you could have very few cells and still obtain a solution, since he's so stable. But the anode then is very big indeed. So the central scheme, much better. Upwind, quite big anode all the time, even with a high number of cells. And of course the anode, if you plot them here, log, anode versus cell size, we know the slope will then be first order for the first order upwind, second order for the central scheme. Any questions to that one?
On the left there. let's say 1,000 CVs, the UDS is letting less pass through than the exact. So it's kind of not diffusive.
Yeah, he's calculating it wrong, you might say.
Yeah.
So here, yeah, the total flux, it says maybe not the best example actually to diffuse something through a solid wall. So, but you'll see it better in the next example actually. But yeah, I can agree with you. He should be diffusive, hence this one should be going that way. Yeah, that would be more natural. Yeah, I agree. But he doesn't. But that's just for this example. Other comments? When did we start? We started half, yeah. 10 more minutes. Yeah, we can take one more. Change the equation. Put gamma equal to 0. Then we don't have any diffusion at all. So we are left only with the convective equation, the convective terms. And here we are in trouble, dead trouble. So we can have a look at it afterwards with the central scheme. Here we have jumped directly to the first order upwind scheme. Now the problem is the one that Patankar called false diffusion example. This one, you send in velocity at 45-degree angles. The velocity field is given, we know that one. And then we say a constant phi on this side, and then a 0 phi down here. And the solution, without any diffusion at all, should be a sharp jump along this diagonal. So the phi should be constant, should be 1 in this area, should be 0 on the other. But due to the mesh system, we will have a sort of a smearing effect here. That's the problem. For the the upwind scheme, we now do it with a first order upwind, very easy. Both u and v, the velocities in the x and y direction, they are constant and they are the same. So you can sort of forget them. They are 0 on the other side anyway. So here we create a derivative taking the central point minus just the western point, because it's now moving to the right. So west for the upwind. And here, the y direction, you take the center point minus the southern point, the down point, because it's transported upwards. So from this equation here, very easy to find a solution. And I believe I have that one ready for you. Should be here somewhere. Yeah. So the upwind should be very easy to calculate, and it's only one swoop for the entire domain, and then you have the solution. So at the point ij, you are only depending on what's to the left and what's under you. That's all. And now I have 10 by 10 points. Yeah, why not? So this is what you get. You have 1 here, and then you will have 0 down here. So here, sort of a singularity over this one cell here, going from 1 to 0. And the solution should have been sharp gradient. Instead you get a smearing out. It might be prettier if we write contour F. And you see it a little bit better. So yes, you get a very strong smearing out of the scheme. So now let's try to get a better solution, and with the upwind scheme, let's try not 10 by 10 cells, let's try 100 by 100. It's a very easy problem, so why not? 100 by 100. And it really doesn't help. You still get this smearing effect, a little bit better, but still bad. And so you can continue using as many cells as you like. It doesn't really get any better. A little bit better, but still the effect is definitely there. Now for the central scheme. He says we have a problem. We can't really solve it directly. So let's have a look at it. This is the equation, and we are going to use now central scheme on this one. So let's try that one. So we have u, and then dphi dx plus v dphi dy equal to 0. That's my equation, and then we do it as easy as u equals v equals 1, and then you can forget about the velocities. Now use a central differencing scheme here. Central differencing scheme, what will it be? Well, for an x derivative, central derivative, we have to take phi I plus 1 j minus phi I minus 1 j divided by 2 times delta x. And for the y direction, it will read something like this: phi I j plus 1 minus phi I j minus 1 divided by 2 delta y equal to 0. Now solve that equation system. But you see, if you write it as a matrix system, you don't have anything on the diagonal. The center point ij is not present. How to solve that equation? So using a matrix method won't work. A direct method, he will explode. It's not possible. So how do we do this? Well, for this example, you can do it since you know everything here and everything here. So you can march your solution forward in space by focusing either on this one or this one, because they will be based on sort of what's happened to the left and down. So yes, it's possible here to create a solution, marching the solution forward in this direction using a central scheme. But in general, it will not be possible to find a solution here with a central scheme, only looking at the convective terms. He will always be unstable. Just for this example, yes, it is possible. And what do we get? What do we get? Go back to 10. And we get something like this. Perfect. So yes, it's not diffusive at all. It's just perfect. You have this jump, and it prevails throughout the entire domain. No smearing effect whatsoever. And increasing now the number of cells, it just gets better and better and better. Just a perfect jump. So yes, the central scheme is of course very, very good indeed here in this case, if you can make it work. So you can look at the code yourself, So I had to sort of scratch my head a little bit here, but yeah, I'll remove this one. You don't need them actually. So it's possible to get the solution sort of straightforward. When you march your inner loops from left to right and from bottom to top. If you had done this the other way around, it wouldn't be possible to obtain a solution. But you find it here actually with one swoop across the entire domain. And we get the same graph. If you look at just how phi is changing from the a line across the center, the CDS makes a perfect jump. The upwind scheme smears it out totally. So the CDS solution that he operates with here, I don't really know where he has gotten that one. Definitely not what I got. I got the perfect one. The upwind scheme smears it out. Yeah, we can have a look at that one. Before, I just wanted to show you here. The conclusion, first order upwind scheme is inaccurate and should not be used. That's the conclusion. Never, ever. Sometimes you use it anyway, but that would then be typically to get a better initial simulation before you then continue with higher order methods, just to have a nice starting point. Because it is very stable, very easy to use, and you get something that might look a little bit what you should end up with. So you could use it to create a good initial state, but nothing else. Now let's go back to this upwind and the central scheme, just to have a look at what we are actually doing, peeking into the modified equations. So here we had the central scheme. And the upwind scheme, UDS. How will he look? Well, then we take the first order derivative to the left. So here I will now have phi ij minus phi I minus 1j by one single delta x. Same goes in the y direction, phi ij minus the point under u, j minus 1, by one single delta y, equal to 0. So now let's do the modified equation. We are going to need Taylor series, phi I, say plus minus 1, phi I, it will then be plus minus delta, phi derivative, plus delta square half, phi double, plus minus, how many do I need here? Maybe I don't need anything more than that. Let's try it. CDS first. The modified equation for this one. You will have here the difference between the two series. And outside we have 1 over 2 times delta x. I have skipped the velocities, so forget about those. So what do we get? Phi I minus phi I, he disappears. And then we have first series minus the next one. So here will be minus minus, which is a plus. So you'll have 2 times of the delta x, phi single derivative. This one, he will disappear. You have plus one series minus the other series, so he will drop. The next one that we will get will be of order 3. So you here it will be something delta x3 phi 1 2 3, like that. And then of course the same in the y direction. What about the upwind scheme? Here we will have 1 over delta x outside, and inside you will have phi ij center point minus the negative series. Center point will disappear, and then we will here have minus minus, which is plus, so that will be delta x phi derivative, and then he will turn out he will be negative since it's a minus here, so I will have minus delta x square half phi double, and the next one will be negative, negative will be positive. That will be something delta x3 phi 1 2 3, and then the same in the y direction. Are the two schemes consistent? Well, indeed they are. When you add in here, you get the phi derivative. The higher order terms here will disappear when delta goes to 0. So we are left with the derivatives, which is what we should have. Same here. Multiply 1 over delta x in, you are left with the derivative. Here you will have the first order term, so he will sort of survive. So yes, both schemes are consistent. And if you rewrite it now, this equation here, you can write it now on the form the x derivative d phi dx, and then of course you get the same in the y direction, equals, and then throw everything else on the other side. It will be now something negative, and we have to divide by delta x, so it will read something like delta x second phi 1 2 3, and also in the y direction, of course. What about this one? Well, you get the original equation back, but now this term put on the other side, switch the sign, divide by 1 delta x, you have something like this. You have delta x half, and then you'll have double derivative with respect to x, and then you will have delta y half, double derivative with respect to y, and then delta second higher order terms there. So there you see what happens. The central scheme, he does not introduce any diffusion. The first order upwind, he creates a lot of diffusion depending on your delta x and delta y's. And yes, if you have very small delta x's and delta y's, this viscosity, false viscosity, actually here I called it artificial viscosity, is then going to be small, but is still going to be present. And as you know, even small diffusion coefficients give rise to a lot of problems. So the modified equation is a very good tool actually to see what's going on. It's really recommendable. Any questions to that one? That's okay. Then we take a break.